Alrighty. So really I want to focus on a particular question. The question I want to focus on is when is effective field theory valid? And in particular I want to focus on that in the context of eternal inflation. And in my opinion, there's some bad news about this question. The bad news is that, as far as I know, we have no working criterion that tells us when effective field theory is valid. Another part of the bad news is that effective field theory is the only tool that we have available to answer many questions. For example, questions in cosmology, questions about the infalling observer in a black hole.
My friend on my right tell me I should say disagree.
Yeah, I would disagree as well, but please go on.
But
Well,
it's not a tool.
at least Eva's work will be mentioned. But what I mean is that in these contexts,
Do you want to take your 10 minutes of uninterrupted time now?
No.
By the way, they didn't even say what they disagreed with.
that's all right. That's fine. I can imagine.
Only.
What I mean is that in these contexts, we don't have available a nice tool like the string theory S matrix that we have in asymptotically Minkowski space, or the boundary correlators in ADS-CFT. Of course, we do have the ability to compute stringy corrections and so on. All right, that's the bad news. The good news, however, and this bad news I think is particularly relevant for eternal inflation. And yeah, if one of the people who disagrees can tell me how to solve my problems in eternal inflation, that's perfect. The good news, though, is that these problems can be diagnosed in a much easier context than eternal inflation, in the context of the black hole firewall problem, which you might not think is an easy context, but we do have many more tools available there that we don't have available in the context of eternal inflation. These black holes can be in asymptotically flat space. These black holes can be in asymptotically anti-de Sitter space. And so we do have some more tools available in that case. But yeah, I'll try to justify my statement that we don't have a working criterion for when effective field theory is valid. So the outline. First, I want to explain why I think it's worth focusing on eternal inflation. Why that's something that's important for us to understand. Second, I want to come to the question, kind of fitting into the theme of this week, of what quantities it is that I want to compute in the context of eternal inflation. Then I'll come to some proposals you'll see that there's some subtleties in how to calculate these quantities. And I'll come to, not in great detail, some proposal for how to calculate these quantities. And what I'll tell you is that there's a problem with all of these proposals of the type that that we're discussing here. And the problem with these proposals tells us that there's a need for new ideas, and there's a need for a better understanding of the breakdown of effective field theory. So let me just go over here. So there's a need for a better understanding of the breakdown of effective field theory. You can kind of see that internally within the context that I'm working. And then I can mention briefly why firewalls are one source of new ideas on this topic. All right, so that's the basic outline. But what I'm hoping to convince you of is, first of all, that it's important to understand eternal inflation, and second of all, that our existing understanding hints that there's something correct that we can get out of eternal inflation, but it's inadequate, and the types of ideas that we'll need to understand the firewall problem are the same ideas that should help us understand these problems. So I think it's worth arguing why eternal inflation is something that's worth trying to understand, since it'll prove to be problematic. And let me start from the most basic argument. The expansion of the universe is observed to be accelerating. And the simplest explanation for that is that we have a positive cosmological constant leading to accelerated expansion. Now, if we believe string theory, we could have also found ourselves in a vacuum with negative cosmological constant. There's no reason to think that these transitions are impossible. So our cartoon, a very simple cartoon, motivated by string theory, is that our situation is something like this. We have some kind of potential, which is actually very complicated. We're sitting here somewhere with positive vacuum energy, but we could eventually tunnel to some region with negative vacuum energy.
Or 0.
All right, so we could also have 0 vacuum energy, and pretty soon we're going to need more dimension in this potential, but that, should we just make it off at infinity there? Right, we could also have 0 vacuum energy. So if we for a moment ignore the decays, so classically, so we seem to be sitting somewhere near here. So classically, we're not quite in de Sitter space right now, but our future is asymptotically de Sitter. And so if I would draw it in a piece of a conformal diagram, here's global de Sitter space. And we could maybe think of ourselves being here, maybe in an open universe like this, or maybe in a closed universe. So forget about the rest of this. We have some piece of de Sitter asymptotics in our future. Okay, now, in fact, in this picture, there's something else that can happen. We can decay. So quantum mechanically, we can decay. But this is a non-perturbative process. And there's a nucleation rate that goes like e to the minus a tunneling action. And so there's a competition between effects, between the classical expansion of the universe and the tunneling. And if this tunneling rate is smaller than the Hubble expansion rate, then we have eternal inflation. So basically the expansion wins. And the volume in the false vacuum goes to infinity at late times. And we have eternal inflation. Now, we don't really know how to compute this tunneling action because we don't have access to the parameters in this potential. This action is sensitive to the height and width of these barriers, and we don't know what those are. So let me draw. So if we are in this eternally inflating situation, then every given, if you follow any given region, it will eventually decay. If we're tunneling to these regions with negative cosmological constant, there'll be some crunches inside there. On the other hand, the volume in the false vacuum will continue to increase. So keep in mind this is a conformal diagram, so the geometry is not represented here. So the volume near future infinity is getting very large, the physical volume. Okay, so we don't really know whether our vacuum will eternally inflate in the future, but it would take an enormous conspiracy in order to have, if what we think we understand about the string landscape is even vaguely correct, we think there's probably some vacuum that can eternally inflate. Some vacuum that satisfies this condition, that its decay rate is smaller than its Hubble expansion rate. And that seems plausible because this decay is a non-perturbative process.
Can I ask for the dimensional factors in that formula? Because I don't actually know how to supply them myself.
Yeah, so this is a decay rate per unit 4 volume. So this formula actually makes sense up to some numerical factor. In this formula, on the other hand, there should be some prefactor.
Yeah, and
what you should calculate here, you should really, I mean, if you want, I could write this as h to the 4th times some dimensionless thing. But really, in order to get that prefactor, you should do some tunneling determinant. Okay? So I think
but
perhaps...
is it h that sets the scale of it or something else? The Planck scale? Or what sets the scale of it?
I would have to think again, but I believe that a reasonable... in the regime where the tunneling happens... So our cosmological constant is rather big. You might think that the tunneling happens on scales very small compared to the cosmological scale because it's a microphysical tunneling. In that case, Hubble shouldn't come in here. So what should come in here is basically dimensionally like the size of the critical instanton bubble. Okay, so or the size of the Euclidean bubble of false vacuum. Unless somebody wants to correct me, but I think this is the typical scale that you would expect there. Yeah?
Has these determinants been calculated for a toy model, for example, of tunneling when you have like two different vacua?
I don't know to what extent things have been done explicitly. So you could start just in quantum mechanical tunneling, and in that case, at least in special examples, you can compute this.
Think of the Coleman-de-Lucia geometry.
In the case with gravity, I'm not sure whether it's been explicitly computed. Does someone know?
I mean, I guess this is only key if we need to decide at the beginning, do we think which regime we're in? Are we like strongly favoring one or the other, eternal inflation or not? I mean, if I were asked to say, I wouldn't know at this point. I have no way to decide, to begin to judge it. Are we?
Well, let me give you one more argument that pushes it a little bit in the direction of eternal inflation. So here's the typical decay rate, okay? And this is some microphysics scale here. Okay, so if these actions are order 1, then the decay rate is not that small. In that case, the lifetime of our universe would have been much shorter than what we observe it to be. Okay, so clearly our universe is somewhat long-lived, and all right, that's not too much of a surprise because you just have to tune this action a bit in order. Right, I mean, you only have to do a logarithmic tuning to make our universe live longer. Okay, so once you tune the lifetime to already be 10 billion years. Then it only takes a tiny bit more tuning here in order to make it 20 billion years or whatever it is that's required for eternal inflation. So the lifetime that we already know, just by the fact that we're still here, already pushes us pretty close to this eternal regime.
I think the prefactor is for the Hubble scale because that's the typical size of bubbles, but the action is much larger than 1. It's exponentially suppressed when you get below, when the potential is below the Planck scale.
Well, so it depends on some detail. Okay, let's discuss the details later.
Once you're below the Planck scale, there's a huge exponential suppression.
Well, it depends a little bit on how big is this bump.
So you could begin to find zero.
All right, so what I want to say is that it's quite possible that in the string landscape there exists at least one vacuum that eternally inflates. Of course, the alternative to this is also quite exciting. You know, maybe there's some conspiracy that in string theory you can never have eternal inflation or something like that. That would be a very surprising correction to naive expectations about tunneling.
Would it mean that if you compute the prefactor, it's always going to be 0 or very small for some reason?
Yeah, well, then you'd basically be saying there's something deeply wrong with this semi-classical picture of tunneling, which would be quite surprising. In this regime that I'm talking about, where this prefactor is not given by Hubble, then gravity is basically a small effect on the tunneling, because the tunneling is basically field theory tunneling. You could go to the other regime where the bubble is quite large, then gravity is important, and then these actions are very large. Okay. So what is eternal inflation supposed to do for us? Eternal inflation, so I'm just going to abbreviate it like this, is supposed to solve two problems for us. The first problem that it's supposed to solve is what to do with this string landscape. Right? String theory was supposed to be this great, unique theory with no free parameters. It turned out to have a lot of solutions. And it's a little awkward to have those solutions just sitting there in theory space, just ruining our ability to predict the mass of the electron from string theory. Okay? And eternal inflation says, at least in terms of the global dynamics, that landscape has a job. The system eternally inflates, and different regions of the global space-time enter different vacua. Okay? So now we'll come to, of course, the question that any given observer can't see this whole region. So that's a downside. But at least in a naive global picture, eternal inflation dynamically populates the landscape. And the region, in the sense that there's big regions of space-time in each vacuum. All right. That's one problem that it's supposed to solve. And a second problem that it's supposed to solve is the question of what are the initial conditions for our universe? And here I mean our universe in the sense that inflationary theorists would normally talk about it. Our local region with slow roll inflation, and so on. So one concrete thing you could have in mind here, for example, is the spatial curvature of our universe. That's a probe of how our period of slow roll inflation began. And we saw yesterday an example where the spatial curvature could quite easily be positive, although it was argued that we would naturally be pushed to a regime where it's nearly flat. For questions like this, in principle, we need some initial conditions for our universe. And in a sense that I'll explain, eternal inflation is supposed to provide those. Okay.
Excuse me, let me ask you something. Is the intuition for the existence of this landscape potential coming from 10 dimensions, or is it known anything if you consider non-critical string theory, for example?
Well, what I was thinking of is just compactifications from 10 dimensions.
I don't think that's...
Of course, there's...
Yeah, I don't think that's essential. In fact, it's just another discrete parameter in the landscape, the total dimensionality. If you start with a positive D minus 10, you have a positive potential energy at tree level. And if it's negative, it goes the other way. So most of the examples will have it positive. Similarly with the curvature, most manifolds are negatively curved and have a positive potential at tree level. I think that goes in the direction Ben is talking about.
All right, so let me explain, first of all, the second point, why eternal inflation is going to help with this problem of initial conditions.
Ben, do you not want to invoke it as a way to understand the CC, or is that implicit in what you said?
Yeah, I guess that's going to be here. So I'm going to come more specifically with what we're supposed to do here. So not only does eternal inflation populate the landscape, but it gives us a way to make predictions, and of course that's the main thing that I want out of it. But let me come to that in a second. Okay, so let's say you have some recipe for initial conditions. So say somebody gives you this landscape, and say they give you, in addition, some recipe for initial conditions. For example, the one that we heard about yesterday. All right, so we have a recipe for initial conditions, and we have a theory that allows for eternal inflation. In other words, a potential where there is some minimum that satisfies this eternal inflation condition. Now, as long as the initial conditions are spatially finite, or have some weight to be spatially finite, then you can argue, and I think Adam Brown is someone who made a version of this argument, then the probability for eternal inflation is greater than 0. Okay, because you start with some spatially finite initial conditions. Maybe they're even in some dumb place like over here.
Sorry, by spatially finite, you mean the universe is compact?
Yeah, let's say the universe starts out being compact, or at least has some probability to be compact. Then there's no boundary condition to suppress a fluctuation to this field value here, and then you can eternally inflate. That's what I have in mind. Of course, you can specify initial conditions that are non-compact. You can just specify that you're sitting in this ADS minimum with ADS boundary conditions. That's perfectly fine, and then you will just stay there. We seem not to live in that universe. So if the initial conditions are spatially finite, we have some probability to eternally inflate. And then we also have some probability that for some history where we don't eternally inflate. Right? Both of those things can happen in general. And depending on the details of the recipe, this probability to begin eternally inflating, so that at the moment I'm thinking kind of in Thomas's language, where you have a probability for different histories. Maybe I should say Thomas, Jim, and Stephen's language. You have a probability for different histories. And the probability for the eternally inflating one could be small. But so if we think about maybe just in this picture, so we have this place that let's call phi f, and we have some place over here, phi 1. So we have a history that looks like this, where we just start, think of this as some kind of sphere. At phi equals phi 1, we roll down and we crunch. That can certainly happen. And then we have some other history where we start with phi equals phi f, and then we eternally inflate, and we make all of this exciting stuff up here. Different kinds of bubbles. There's some probability for each of these. Now, what I think is a plausible assumption in this context is that the place where we live in this probability distribution is where most of the people live, which is at late time in this eternally inflating history. Yeah?
Where did the probabilities come from? I mean, where did probability creep in here?
These guys?
Yeah.
Well, you gave me those.
What?
You gave me those.
No, they're quantum mechanical probabilities.
That's right.
Wait, so you need to assume Parnell-Hawking, say, as a initial state there, or?
Well, I just want some recipe for initial conditions that will give me a non-zero probability for this history. And then I claim that the thing we should focus on within this distribution is the late time asymptotics of the eternally inflating histories.
So does the choice of wave function wash out? Is that what you're saying? Or
Yeah, so the assumption is going to be, so we have there's some probability for these finite histories, and I don't really care about those because most of the people are in the infinite histories. All right? This is incidentally not something I could derive, like philosophers of probability will probably argue about this, okay? So that's why I listed it as an assumption. But I think the natural thing to focus on, if we have some probabilities for different histories like that, is this region up here at late time in the eternally inflating histories.
okay, sorry, one more question. The rounded one is one that doesn't actually decay.
This is one where we just, so we just started here, and then we just roll down, and then we crunch.
So it does crunch, even though you didn't draw it. Then on the right, the rounded one where we live.
Oh, this one.
Why is it rounded? What is that supposed to mean?
Oh, yeah, that's some other de Sitter space inside there.
And it doesn't. That de Sitter space doesn't decay.
Oh, sorry. Let me be more specific in my assumption. So we live somewhere in here, in this late time region of the eternally inflating.
The rounded thing is supposed to be a de Sitter that doesn't decay.
Oh no, it'll decay. Okay,
Doesn't
there's
roll
some other stuff here.
Okay.
Yeah. Yeah. Yes.
The question. All these pictures are strongly time-oriented. Presumably the fundamental theory is not time-oriented. What is it that breaks the T reversal invariance in this picture?
Well, I'm assuming here that Jim gave me some initial conditions that are on some compact, that at least have some weight on a compact spatial surface. And then the time evolution kind of makes things more complicated because of the second law. So it's in this way of thinking about it, it's the initial conditions.
Which is still special in some sense.
Yeah, that's right.
So Ben, I mean, so you say eternal inflation is supposed to solve the problem of the initial conditions, and your solution is we're always in this eternally inflating regime.
Yeah, exactly. My solution is I think it's natural to focus on this region here, and in that region it doesn't matter what these. So this has some probability P1, this has some probability P2. And you can even imagine different initial conditions down here that all lead to eternal inflation.
But you just agreed that it's a special initial condition, didn't you?
It was a spatial initial condition. Yeah.
But my question is, this looks very classical, right? This doesn't look like a quantum state to me. This looks like you've written some classical solution with some tunneling to other classical solutions.
Okay, good. So that's a good question. So let me try to be more precise about this, okay? So given this initial condition, eternal inflation will very likely happen. When eternal inflation happens, you'll get some superposition of different geometries that look like this, right? So really what we'll have, so probability P1 will have this boring thing like this. Probability P2 will have eternal inflation. And eternal inflation really means a superposition of this thing plus something where the bubbles are in slightly different places. So let's just say plus other eternally inflating realizations. Right. So and of course there's many of those things.
Shouldn't we be here in an empty universe today because of eternal inflation starting, say, before the last phase transition?
Can I postpone that for a moment? That's a non-trivial question you can ask, but I think we're not quite there yet. So one thing that I want to use is that eternal inflation has an attractor behavior. As long as it's similar to the de Sitter no-hair theorem, which is that the late time configuration, or the probabilities, let's say, for different bubbles, is independent of the initial conditions.
Provided it's special.
Sorry?
Provided it is special in the sense you said before.
Yeah, so for concreteness, let's say the initial conditions are given on some, maybe I could relax this, but a case where I know it's true is, let's say the initial conditions are given on some compact spatial slice. Then this is a true statement. In the same sense of the de Sitter-Noether theorem, on extremely long scales, you can still remember the initial conditions. For example, whether you start on a torus or whether you start on a sphere. But in terms of the local stuff that's going on, the probabilities for different types of bubbles, it's independent of these initial conditions.
Could I ask one more question which I should have asked before, which is, should I think of the landscape as the collection of all the minima in a fixed potential, or as an ensemble of different potentials?
Now let's say that there's a fixed, very complicated potential.
Okay, good. So if, for example, that potential doesn't happen to have a negative cosmological constant, then that'll affect what you see up at the top. Right?
That's right. But the one thing we think that we know is that we do have minima with negative cosmological constant.
So will you come to the question of how we actually define probability in this whole future?
Yes.
That's on the agenda.
That's right. That's right.
So then,
yeah.
That is independent of initial condition, but it depends on what you call time, right?
Well, that's. What do you think is coming? Like in, I erased the outline. Okay. Okay. Right. Yeah. So a subtlety is going to come in here, but let me say what seems to be good about this picture, which is that first of all, we can forget about these. We can forget about the initial conditions that came to us, that Jim gave us. Those aren't relevant. We just have to characterize this attractor behavior up here. And in particular, the initial conditions for our universe are given by where we tunneled from. Okay? So the initial conditions from our universe, so let's say our local initial conditions, question of what was happening before slow roll inflation started is that we came from eternal inflation. All right, that's what is in our past.
But the probabilities for those initial conditions are also given by James Wafer.
Sorry?
Because the probabilities for those initial conditions are also given by James Wafer.
No, what I claim is that we should characterize the late time real time dynamics of the system, and in certain special cases that will actually be equivalent to something like the Hartle-Hawking wave function, but in general it won't be. In general, it will be. In general, it will be quite different. Sorry?
The wave function provides probabilities for histories, and what you're saying there is an example of a history.
That's right. But my point is that these infinite histories, their late time dynamics, say the number of bubbles of different types, is independent of the initial conditions. And so the initial probabilities that you get, sorry?
A lot of intervening stuff, right?
Absolutely.
Yeah.
But that's part of the probabilities of the histories.
Okay. That's true. Okay, so look, formally this would also be contained in the wave functions you were writing down, at least before you coarse-grained. However, I'm saying that we can access this in a simpler way by just understanding the late time, real time dynamics.
That's the coarse graining I was talking about yesterday.
Okay, that's not very clear whether that's the same thing. I think that it's not, because I want to keep track of all these bubbles.
There's an important distinction, though, which is that you're not assuming the Hartle-Hawking wave function here. You're taking initial conditions, which is that there's something there, and in some region, which is different. I mean, it's important that will give predictions which are not the Hartle-Hawking wave function.
But I don't care. These initial conditions could be given by Hartle-Hawking, and then.
No, but the Hartle-Hawking wave function will just be a delta function on some negative CC vacuum.
No, that's
okay.
Zero CC. I mean.
All right. There's many interesting things that maybe I think it would be more productive though if I would go forward though. So one idea is that the local initial conditions are given by eternal inflation, and this is something that we could get some observational evidence for, because if we observe positive curvature, say in the next generation of experiments, in other words, we observe that we're living in a part of a sphere. So if we observe positive spatial curvature, the quantity is called omega k, then that would rule out this picture that our period of slow roll inflation started from eternal inflation.
No, you could still have chaotic eternal inflation.
No, not if you have positive curvature at a level larger than 10 to the minus 5. So this rules out the idea that eternal inflation is in our past.
So that couldn't happen as a kind of local fluctuation, and I mean.
Well, everything is probabilities, but if we would detect curvature at the level 10 to the minus 3, which is consistent with certain data, that would be unlikely at the level of e to the 100.
Okay, okay.
And so I would feel comfortable ruling out eternal inflation.
That's really cool.
On the other hand, and if you see positive curvature, then some picture like the ones that Thomas was drawing, although with some different details, I guess, would be more the thing that you would be looking for. On the other hand, if we observe negative curvature, then that supports this idea. Because if slow roll inflation began by a tunneling event, which is very natural in this context, then we could have observable negative curvature.
So that's true, but it also could support just the topology of the spatial slices globally being some compact hyperbolic space for some other reason.
That's true. And the most likely thing is that we'll never observe the curvature, and then we won't have any. So, okay. At least you could rule out this proposal at a high level of confidence by observing positive curvature. All right. So this is one thing that we want to get out of this. The other thing that we want to get is a recipe for making predictions in string theory. We want to make these predictions by counting. So the probability of two different experimental outcomes, say detecting superpartners in the next run of the LHC or not detecting superpartners, is given by counting. So all we need to do is understand this semi-classical evolution. We need to count events of different types. So we can count the number of LHCs that detect superpartners and that don't detect superpartners in the multiverse, and then that'll give us our probability of detecting superpartners. Okay? That's a proposal. It sounds crazy, but I'm not aware of any competing proposals. So, I mean, even the stuff you were doing is basically in this category with some differences in how it's implemented.
No. It's not counting. This is not a quantum mechanical notion of probability.
That's true. I mean the semi-classical approximation.
Not even semi-classical.
Interesting.
Well,
all right.
Semi-classical backgrounds, yes.
So my prediction, I just want to interject one more modest thing, which is, quantum field theory makes a lot of predictions once you specify the content of the field theory that you're dealing with for a particular system, and then you get a lot of predictions. And we can be more modest about predictions in string theory without having, any universal global predictions by modeling physical phenomena where string theory is relevant using, the way we use field theory. So that's more modest than what you're trying for, but it's maybe a little more realistic as a way to make contact.
Yeah, I agree. Right. I mean, aside from this particular question, the asymptotics of eternal inflation, they're interesting. They're nice. They have this attractor behavior. They have this richness of tunneling. They have the flavor of something that we could try to understand in string theory from the point of view of some sort of dual theory. Okay? If there's no tunneling, then they're just like the ADS boundary, more or less. And the idea of a dual theory living at future infinity is very attractive, and it's been hard to really make concrete. And, in order to have really well-defined quantities in string theory, we're always trying to throw things in from infinity. And the eternal inflation asymptotics, they're the best that we can hope for. Because unless we violate the null energy condition, we are not living in asymptotically anti-de Sitter space. We are not living in an asymptotically Minkowski space. As far as we know, we could be living in an asymptotically eternally inflating space-time. So the best boundary conditions that can be connected to us are the boundary conditions, are the best asymptotics that can be connected to us are eternally inflating asymptotics. Okay? So even if all of this is the wrong idea, there should be some nice description of this system. Yes?
Well, usually in talks like this, when you get to counting, then somebody says, well, you have to have a measure to define.
Yeah, okay, so now I come to the measure.
Oh,
well, because Yisheng already said it, that it depends on the definition of time.
Okay.
Yeah. But,
I didn't mean to interrupt your talk and say you have to do it now.
from the point of view of observables and so on, maybe these things are the wrong thing to compute, but I think there should be some right thing to compute about eternal inflation. And I'm very interested in whether someone has a different idea for what that is.
And can you just explain why that equation that you wrote down is like non-tautological, or I just don't understand the content of that equation. PA over PB.
This one?
Yeah.
Yes, good. Sorry. So I think I said it in words, but so say we want to make some prediction for like whether we're going to detect a negative curvature with the next mission. We should, in order to make the best prediction, we should put in all of our data. Although you don't, in practice, you would never really do that. So you put in all of our data, and then you just count. So you know how to simulate this thing in your computer. You have the landscape.
So
and then you just
count all of our data.
Well, in principle, everything that we know.
In our universe?
Yes. But you simulate this bigger thing. Okay? And then you just count. How many places are people detecting negative curvature? And how many places are they detecting no negative curvature? Then you can decide whether to fund this mission or not.
You're just saying that we'll do our best by just plugging in what we know. We don't... Is that
Yeah.
what you're saying?
Well, that's right. More generally, what I'm trying to say is we should expect to see things that are common in this late time attractive behavior of eternal inflation. Okay, so like certain types of bubbles are more common than others because it's easier to tunnel into those, and we should expect to live in those types of bubbles. Okay, so you could apply this to, for example, the cosmological constant. There you're asking a slightly different question. There you're saying, let's forget about some of what we know. Let's say we don't know the cosmological constant, and let's put in some aspect of what we know, and then let's ask whether our value of the cosmological constant is a common value or an uncommon value. So that's a way you can test the theory. All right, so this...
Excuse me.
Yeah.
To do a calculation in this framework, what do you need to know about the theory? Do you need to know the shape of the potential? Do you need to know how many minima there are? What do you need to, what's the inputs?
Yeah, I need to know everything about the potential. And as you'll see, I need to know something else too. And that's the problem. So one problem is that we don't know everything about the potential. That's a kind of a minor technical problem. Another problem is what I'll come to. Okay.
Do you put any anthropic principle, like a lower bound, an upper bound on the cosmological constant?
Well, when you're asking, there's different types of predictions you could make. If you want to make true predictions, you're going to put in everything we know, so then there's no point in putting in any additional anthropic principle because you've already put in that we're here. If you want to test the theory, it will make sense to put in some anthropic principle, so you could ask, given that we're some intelligent life, what's the probability of seeing this value of the cosmological constant versus some other one? You could also try to ask just an unconditional question. Given that we're some random place in this eternally inflating space-time, how likely is it that the cosmological constant is the value we observe?
But that's related to my previous question. I mean, what before the phase transition, the last phase transition, either the QCD or the electroweak phase transition, the vacuum energy was certainly not the one it is today.
Sure.
So I don't see why one of the minima couldn't inflate forever at that scale.
It could, except that it will, just because of quantum mechanics, because it will tunnel eventually.
Well, according to your criteria, there can be something which keeps expanding.
It does keep expanding, but locally it tunnels.
Okay. But and we will be where it tunnels.
Well,
we are living where it tunnels, not where it expands.
I think that it makes sense to focus on the places where interesting structures can form. There will certainly be many places in this diagram where no interesting structures can form because things are just inflating very fast.
We do use that.
Those will certainly be there.
Okay.
I don't think those are a problem, but you could decide that those are a problem. Okay, so here's the quantity that I want to compute. And aside from this question of making predictions and counting observations, I just want to calculate the number of different things at late times. And it could be the number of different bubbles of different types, the number of observers of different types, or whatever. And you can see that this is a bit dangerous, trying to count things, because the space expands, it gets infinite, and NA and NB are both infinite. And so you could try to take a late time limit. You could count the number of events of each type before some time and define the ratio that way. So you can take this picture and you can try to draw some time cutoff on that picture. But as Yisheng said, there's a lot of different choices of time variable, and the answer depends on the choice of time variable. Okay, so
Ben, is there any way to say that you take a set of local observers, each of them takes cosmological time, and then you connect it somehow? Is that
yeah, so that would be one proposal for a time variable, and I think it's worth mentioning. So one thing you can do is, I'm not sure what you meant by cosmological time, but you could do something called proper time. So you just start with some initial condition. You draw a bunch of geodesics like this. Then you have all of your eternal inflation stuff. And you just cut this off at some value of the proper time. Okay, some tau equals tau 0. Given proper time along each of these geodesics. And you cut that off. That would be one choice of a time variable. Unfortunately, there's also other choices. And in particular, as long as we're in effective field theory, this theory is diffeomorphism invariant. There is no preferred time variable. Okay? So as long as we're within, say, semi-classical gravity, then this ratio that I was trying to define is just not gauge invariant. It's not a diffeomorphism invariant quantity, right? In some sense, characterizing the late time behavior of eternal inflation can be done in a diffeomorphism invariant way. There's just some local dynamics that characterizes that space-time. But counting the number of events of different types, since it depends strongly on the choice of time variable, and there isn't a preferred time variable, this quantity just makes no sense. So at this point, you have two choices. So the proper time variable would be one choice. That's not what I meant. So this quantity is not gauge invariant, let's say, in the effective field theory description, or in the semi-classical gravity description.
That it becomes better defined once we go out of effective field theory.
So you have two choices. Okay? Choice one, for the reasonable people, choice one is that this thing is the wrong idea. Okay? And this is just not what we should be calculating. In that case, what is the right thing that we're supposed to be understanding? Should we just forget about understanding eternal inflation? That's certainly a possibility. Maybe we live close to the initial conditions, whatever they are. Or are we supposed to understand eternal inflation in a different way? Okay? But there's certainly a possibility that this is a wrong idea. Then I just want to know what is the right idea. Okay?
I'm sorry, but isn't there a diff invariant time if everything started with, say, the Hartle-Hawking wave function, and you can count the number of decays back to the beginning?
No. I'll give you a more explicit example in 1 second. Okay?
Why is the proper time to the event along that doesn't work?
Okay, let me give a more explicit example now. So one choice, to be explicit about the dependence on the time variable, one natural choice is you just start with whatever your initial conditions are down here, and then you cut things off at a certain proper time along these geodesics. That is certainly a well-defined procedure.
Oh, I'm sorry, those geodesics will cross. I'm not sure. Why
Okay. It's well-defined up to some caustics, then you can have some recipe for what you do at the caustics. It's not a big deal, okay? It's not the biggest deal. Okay. Okay, so limit of the proper time goes to infinity, NA over NB. That's a quantity you can define. Okay, no problem. Another thing you can define is you can define a thing called the scale factor time, basically a time variable that measures the local expansion rate. Okay, so more concretely, you would have some geodesic congruence. You would measure the expansion of that geodesic congruence, and you would use that, define that to be your local.
But your reference surface is not well defined, so these are not well defined.
No, you just start here.
Where's
You start at your initial conditions. This is your initial condition surface.
That's breaking different.
Well, okay, you could have made that. Somebody gave me a theory of initial conditions, and that theory of initial conditions. Let's say for simplicity that the initial conditions are just on a spatial sphere of a given size.
Finding things relative to, say, some initial quantum phase, or something
That's
as a
basically
state.
what I was saying. If you've got, like for example, it came out of the Euclidean regime in the Hartle-Hawking wave function, and then we can just count the number of decays. That's a natural.
The issue is the late time divergence in the number of decays, and how you regulate that late time divergence.
But Ben, are you saying it's not diff invariant, or are you saying that they're different diff invariant prescriptions?
Well, that's maybe another way of saying the same thing. Go ahead. What did you want to say?
I don't get to say anything here. Usually, if you think about the analogy with holography, then and certainly with Euclidean ADS, then these divergences we regulate, but there's kind of a physically interesting finite part to the ratio. Is that maybe what we're after?
Yeah, I think that's an interesting idea, and I'll say a little bit about that in a moment. So you can also define something called the scale factor time, which is basically using the local expansion as a clock, which you can define. And you can also, so let's call that thing t. And then you can take the same thing, t goes to infinity. T0 goes to infinity. You can also define that thing. And it will give radically different answers. Okay? If you use this time variable, then most of the spatial volume will be taken up by the fastest inflating de Sitter vacuum. If you use this time variable, most of the spatial volume at late times will be taken up by the longest lived de Sitter vacuum. Which in examples would be, that would be radically different even in a simple example where you have something like this. Just two de Sitter vacua. Okay, these two different recipes would give radically different answers. Okay, this proper time cutoff is telling you that most of the volume is here, and the scale factor time cutoff is telling you that most of the volume is here.
Okay, but again, these could, I presume, well, the first one I think you can give a different variant prescription for. The second one you probably can as well, right? So these are, with diff and variant, they're just different prescriptions.
It's true. Okay, so
they are gauge invariant.
You can either say like this thing is not gauge invariant, or you could say there's a lot of different gauge invariant ways you could define this thing.
Yeah.
Which is just as bad.
I agree. It doesn't sound very good.
Yes.
So why don't you just say the theory consists of this potential, right, and plus some measure, and then you test the various measures against the observations.
Exactly. So the second, the first possibility is Mark's idea that this is the wrong idea. The second idea is that quantum gravity tells us a preferred regulator. One version of that is that there's some dual theory living on future infinity, and this is some IR divergence in the space-time, and it's dual to some UV divergence in the field theory, and there's some preferred way of regulating that UV divergence. So this is the second option.
But sorry, that field theory does not decouple from gravity, right? You can't get away from the fluctuations.
Yeah. So I'll say a little more about how strange this field theory at future infinity would have to be.
I mean, it's not just a pure quantum theory.
Yeah, that's right. Right. So then this would tell you that the semi-classical analysis breaks down. But we could be in a situation where we could imagine some landscape where none of the energy densities are particularly high. Right? We could at least imagine that the Planck scale is way up here and everything is happening at lower energies. So there's no obvious reason that the semi-classical analysis should break down. So is there any motivation for thinking this crazy idea number 2, that this quantity can actually be regulated? Is there any reason to think that effective field theory should be breaking down in this situation? And I think that there is.
Are those the only 2 alternatives?
Yeah.
I mean, isn't a third sort of, well, that the theory of quantum gravity doesn't allow all this nonsense at some level?
Yeah.
We're talking about positives. Well, is it really?
Okay, well, let's just put it here. Eternal inflation is the wrong idea.
Right? For example, quantum gravity is not required to have a landscape.
No, that's right. So, but let me just put that in the category of eternal inflation. It's not the right idea. You don't need a big landscape for this to be an issue. It's enough to have one eternally inflating vacuum.
Well, would you call what we have today, if the cosmological constant is positive, the beginning of an eternally inflating phase or not?
Yeah.
Okay. So let's say, so there's something else. You could have a positive cosmological constant today, which we take to be the beginning of eternal inflation, but maybe you don't have all the other story with multiple vacua, et cetera, et cetera.
Yeah, so then I would say you're going to have some excuse why eternal inflation is the wrong idea. Like we have some other initial conditions. We're living near the beginning. We rolled down. Here we are.
Getting here by eternal. Yeah.
And then who cares about all this eternal inflation that happens later?
Eternal inflation,
not our problem.
As an initial condition is the wrong idea for us.
Yeah, so that's basically saying eternal inflation is not relevant to understanding anything that we see.
Didn't we start out with everything compact?
In this case, it was compact, yeah.
Where did we get to infinity over here?
This infinity is coming from the late time dynamics.
So it's like the bacteria? Is that what?
Yes. Indeed. Okay. So there is a reason to think that this semi-classical analysis breaks down. And the reason, one way to motivate it is by an analogy with black hole physics. We know that in black hole evaporation, we need to have violations. So we know that in black hole evaporation, we need violations of effective field theory in regions. So what would be, so I wanted to focus on this question of violations of effective field theory. So the naive answer is that effective field theory is fine as long as the energy density is low and the curvature is low. But we know that in order to get unitary black hole evaporation, we need violations of effective field theory in regions where the curvature, basically in regions near the horizon, while the black hole is still large, so in regions of low curvature and energy density. Right? And a recipe there that worked for a while was this idea of black hole complementarity. There's an additional requirement. The additional requirement was that we describe one causal patch. So, in other words, a region that in principle is accessible to a single observer. On the other hand, you can see that this divergence here is coming because we're trying to describe eternal inflation globally. Okay? So, based on this analogy, there is a reason to think that the semi-classical analysis is breaking down here, even though locally the energy densities may not be large. Right. So I think another way of stating this issue is that we think that the de Sitter entropy is finite, and yet we're describing some infinite number of patches there. Okay? So there's something a little bit fishy about how many degrees of freedom we think we need in the theory versus the number that we're using to describe this whole infinity of different regions. And so for a while we had fun playing this game that Jim just suggested. So let's make a guess. Let's make a guess that quantum gravity regulates this divergence. And when we go down to the low energy limit, what this gives us is the usual semi-classical dynamics with tunneling and so on. Plus some cutoff description. Plus some prescription for how to regulate this cutoff. Now, this cutoff prescription, if you think that there's some kind of duality, the cutoff prescription in the bulk is equivalent to a UV cutoff prescription in the field, in the dual theory, whatever that may be. So this is a light time or IR cutoff in the bulk. And that's dual to a UV cutoff in whatever dual theory you might think is living there. Let's say in the thing that's not a CFT. Now, I just want to emphasize that this quantity that we're hoping to define, it's a very strange quantity if this was anything like a field theory. Because this quantity, NA over NB, it's dominated by the late times. Right? In the bulk, that's due to exponential expansion. We understand why that is. From the dual point of view, it's dominated by stuff that's happening at the cutoff scale. Okay? It's happening at late time stuff, which means stuff at the cutoff scale. So this is like a non-universal. This is dominated by lattice scale physics. So if this dual theory is any kind of conventional field theory, this just has to be the wrong kind of observable to be calculating. Okay? On the other hand, we know that because of, for example, the reason that Eva was saying, we know that this dual theory has all kinds of weird things like these bubbles with zero cosmological constant that poke holes in it. So I don't think it's so crazy to think that, well, this is some kind of other thing that's not a field theory, and it comes with its own preferred regulator.
Right, and even before you get to the poking holes, you don't decouple gravity because to compute all the observables, you have to integrate over that metric. So.
That's right. So this is a very exotic dual theory. I just want to emphasize that this is some kind of strange observable. Okay.
I'm sorry, what space is this dual field theory supposed to live on?
Future infinity.
It fluctuates.
Some fractal, future
Yeah.
infinity is really,
It's a mess. Yeah, it's a mess.
it
Yeah.
lives on that really fractal type geometry is the idea.
That geometry also fluctuates. You have to integrate over it if you can make sense of that.
It is that fractal geometry
It's a theory
plus
of that
some.
fractal
It's a theory of that fractal geometry plus some other fields on it.
What kind of gravity is it?
Some Liouville, conformal gravity, whatever. I don't know. You tell me.
So it's not Einstein gravity. Did you?
I don't have this theory. Do you?
I apologize. I'll shut up. No.
I think there's some free time tomorrow when you could describe this theory to us.
Actually, the point, regarding time, how much longer do you need to finish what you brought?
Well, a lot of time, but let me just wrap up before cookies.
Yeah, that sounds good. And then we have time for discussion.
Cookies are an important.
Cookies too, so,
Yeah. I will definitely stop talking at 3:15. Right. So we played this game then of just guessing different cutoff prescriptions, and so now you're playing a simple game. Okay, you just want to calculate relative numbers of different types of events. You want some recipe for cutting off the infinities. So you can look at these different, and you want some recipe for cutting things off that makes sense in every part of the landscape. So for the most part, that's some kind of geometric prescription for cutting these things off. And you can show nice things. For example, you can show that this proper time measure predicts that we should live much, much earlier, much closer to our local Big Bang. And so this one you can just rule out by comparing to observation. Okay, so that was a fun thing to do for a while. And eventually we had some prescriptions that were, as far as we could tell, in agreement with observation. There's still some non-trivial checks on properties of the string landscape. And one of them that's still an acceptable measure is this scale factor time. And that's equivalent to some kind of causal patch cutoff, which will be important to make this connection with the black hole physics, which basically says we're just going to count things within one causal patch. In fact, it has some ensemble of causal patches that was related to this UV cutoff. And at the level of precision here, it's more or less equivalent to the scale factor time.
I'm confused at how's that UV cutoff even playing a role, because you already had that definition without talking about it.
That's right. So one way to try to regulate this infinity is to define some kind of UV cutoff on the boundary and then translate it to the bulk. But you don't have to do that. You could just say, I'm just going to work in the bulk. I'm just going to define my geodesic congruence, cut things off, and that's perfectly fine. And then you can show there's some equivalence between this prescription and some prescription for what you're doing on the boundary. But you don't have to refer to that dual theory. So here's one cutoff that was motivated by this black hole analogy. Let's try to work in a region where effective field theory is valid, and let's just count things in one causal patch. Right? Seemed like the right idea. And in fact, this program had some successes. One of them is getting rid of some of these measures. And another one is, in the measures that survived, you can explain in a robust way the cosmological coincidence problem, the question of why we're living at the time why we're seeing the energy density, the vacuum energy, about equal to the matter density. You can explain this in a rather robust way with some plausible assumptions. But what I wanted to tell you actually is what's wrong with these cutoffs. What's wrong with these cutoffs is not a conflict with observation. These cutoffs have a conflict with local physics, with naive local physics, or let's just say they have a conflict with common sense. And to see this, I'm going to tell you about the following strange type of experiment that you can do. This is described in more detail in a paper called Eternal Inflation Predicts That Time Will End. And a couple of my collaborators who are now doing more respectable kinds of physics were co-authors on that paper, Stefan Leichenauer and Vlad Rosenhaus. So they might not want you to ask them about this work, but they are experts. So here's the strange kind of experiment. So I'm going to put you in a cryogenic freezer. And then I'm going to flip a coin. I'm going to flip a fair coin. If it's heads, then you sleep for 1 year. And then you get thawed out. And if it's tails, then you sleep for 20 billion years. Okay? Now you wake up. And you get a chance to bet. You want to bet whether you slept for a short time or a long time. Now, if I ask most of you to bet on this, you'll probably bet around 50-50 because this coin is fair. So, common sense, or local physics, tells you that this is a 50-50 proposition. On the other hand, if I do this to Alan Guth, I put him in the freezer, he will take into account eternal inflation, and we've defined how to calculate probabilities. So if you use our eternal inflation recipe, in fact, any of these geometric cutoffs, you can kind of see what's going to happen. We assume in this eternally inflating space-time, sometimes it happens that people take short naps, and sometimes it happens that people take long naps. And when you count the people that wake up, this is our prescription for regulating infinities. We forget about everything that's outside here. And you can see that when you regulate infinities in this way, then more people wake up after short naps than after long naps. And so here you find that the probability of a short nap is much longer than the probability of a long nap. Okay? So this is not a conflict with observation. In fact, this is a similar thing to what helped us explain this coincidence problem. But it tells us that something about the way we imposed this geometric cutoff was too crude. Okay? We simply threw out all of the events outside. So there's a simple interpretation. It's not the only interpretation, but there's a simple interpretation of these probabilities. You know, why? Oh, sorry. The simple interpretation of why you should bet that you had a short nap is that there's some danger that you fell out of the causal patch, and falling out of the causal patch, time ends there. Okay? So in other words, a simple interpretation is that this cryogenic freezer is not as safe as we thought, even though it seems to function perfectly. It has a danger of running into this cutoff and time ending. Okay? You can give...
So you can't remove the regulator, is what you're saying?
Yeah, so you would think like if you take one of these time variables, that I erased, you're taking the limit that time goes to infinity. So surely that this will go away. But the problem is all of the physics is always happening very, very close to the cutoff. If you count the people waking up, if you assume you're typical among the people waking up, most of the people waking up are very close to the cutoff. So even though you would think that this effect would go away, it does not go away.
Why don't you take the not till everybody is woken up cutoff?
That's right. But the problem is people are always waking up and going to sleep in eternal inflation. So then you need to make some special rule that your cutoff, then you're in the business of kind of modifying your cutoff in some way. So that it never passes through any people. But then it becomes very complicated, and there didn't seem to be any simple way of doing this. So my point is not this interpretation. My point is our cutoff disagreed with naive local physics, and it disagreed on a time scale of Hubble, 20 billion years. A time scale where it's not really acceptable to have this big disagreement with local physics. And so this is a problem with this measure, in my opinion. This is a problem with these recipes. And it's telling us that we were too crude in just cutting this off. And instead, we need to really understand what's going on. We need to maybe use effective field theory a little bit outside the horizon and understand how these operators are starting not to commute. And the firewall thing kind of comes from the other side. It tells us even within one causal patch, we need to have a violation. In order to preserve unitarity, we need to have a violation of effective field theory. Okay? So I think both of these things are pointing in the same direction, that we need to understand the violation of effective field theory, and we need to understand the physics of that in some more detailed way than just excising regions of space-time. Then we have a chance of understanding this correct measure of getting rid of this paradox and hopefully also understanding the firewall situation. All right. Well, I had other things to say, but thanks.
Any very pressing questions?
Are we coming back?
We are coming back, those who choose to.
Maybe you should say, is it just discussion about anything at what time? Or?
Well, so yeah, there is discussion, and I think there's some unfinished business. Gathering from what you just said, I think Thomas has unfinished business, but there are also some other things we could discuss, so we'll work it out.
And at 3?
Oh, it's at 3:30, right?
But maybe we can delay it until 3:40?
People want to. People want to delay till 3:40 or go at 3:30? Okay. How many want to delay? Not many. Okay, 3:30 it is.